All right, everybody, welcome back to chemistry. And so now we're leaving chapter 11 and we're going into a new chapter, chapter 7, which is about gases. And so the first thing I want to do is I want to look at how certain properties of gases are different than that of solids and liquids. And so there are a few important examples here. So one important property of gases is that they have an indefinite volume and an indefinite shape, and they can pretty much fill the volume and shape of their containers at will. So let me explain that with this sort of simple example here. So let's say here we have a flask, and let's say this flask is evacuated at this present time and there are no air molecules in here. And let's say within the flask we have a beaker, and the beaker has a watch glass on top of it. And so basically the watch glass is covering this beaker and it sort of seals this beaker for now. And let's say that within this beaker we have air. And so here are the individual air molecules that are there. So let's say that we shook this beaker in the flask and shook it enough so that the watch glass broke. What would happen? Well, you probably know what would happen is that all these air molecules would fly out of the beaker into the flask, and they would expand into the flask. Now, when they were in this beaker, they were contained in a certain volume and they had a certain shape. The shape was that of the beaker. But when they expanded out into the flask, they changed their volume. Their volume increased quite a bit because the volume of the flask is greater than the volume of the beaker. And they also changed the shape. They followed the shape of the flask instead of the shape of the beaker. And so because of this, what you can say is that gases have an indefinite volume and an indefinite shape. Now, let's say you were to compare that, say, for example, to a solid. So imagine that we have, instead of gas in this beaker here, we have a solid. So let's say it's like a chunk of granite. So you know that the granite is made of atoms and molecules. And you know that although the atoms and molecules are sort of vibrating in place in the granite, they're really, the molecules and atoms are not able to move past each other. So they're pretty well stuck to one another. And so for this reason, solids have definite shape and they have a definite volume. Now, with liquids, it's a little bit different. There are some bonds between the liquid molecules, but there's not as many bonds as you see with the solid molecules. And what that allows the liquid to do is to have an indefinite shape that can flow to whatever the shape of the container is, but they still have a definite volume. But again, gases, because they have no bonds really between the molecules, they have an indefinite volume and an indefinite shape. Okay, so another important property of gases, which is different than solids and liquids, is that gases are considered compressible. So if you can imagine how easy it is for gas molecules to leave this beaker and to expand out into the flask, then you could probably surmise it's probably easy to apply pressure from the outside onto a gas and compress its volume. You can't really do that with solids and liquids. The molecules in solids and liquids are relatively close to one another, and for that reason, it's very difficult to compress solids and liquids into a lower volume. Another sort of important property about gases is that if you have different kinds of gases, they mix together in a container thoroughly and evenly. So let's say here in this flask here, which is stoppered, I'm going to add a syringe. So here is the syringe here. And let's say I have a plunger here on this syringe. And let's say I have some different kind of gas here. I don't know what it is, but we'll say it's pink. While here, the gas in the flask is the air, which is in blue. And so let's say you injected this pink gas into this flask. You know exactly what's going to happen. It's because these gas molecules are traveling very fast. Very quickly, these pink gas molecules would intermix very well with the blue gas molecules. And then in the end, what you'll have is you'll have the gases completely mixed in the same container. Okay, now another important property that we have to look at for gases is their densities and compare them to liquids and solids. So I want to spend some a little more detailed time on that. So I'm going to go over here to the computer to explain that. Okay, so let's look at three substances. We have water here, and we have benzene, and we have carbon tetrachloride. And so what I want to do is look at each of these three different substances in their three different phases. And so we're going to look at, for example, water in the solid phase. We're going to look at the liquid phase and the gaseous phase. And what we're going to do is look at their densities. So let's kind of focus in on what the density of liquid water is first. And so you can see water at room temperature has a density of 0.998 grams per mil. Now, interestingly, it is not 1.0 gram per mil, which kind of raises the question, is there a temperature that you can bring water to where it would get to a density of 1.0 gram per mil? And that temperature is known, it's at 4 degrees Celsius. So when you raise the temperature of water from 4 degrees on up, it tends to have a lesser and lesser density, but not by much. Now, if you were to cool the water down and so it became ice, it would be in the solid phase. What you may know already is that the density of solid water in the form of ice is significantly less than the density of liquid water. It's about 8% less, and so it's about 0.917 grams per mil. So that sort of explains why solid water, which is ice, floats on liquid water, because ice has less density than liquid water. Now, here's the remarkable thing. If you take liquid water and you boil it off into a gas, its density decreases by about 1,500 times. So it's only a small fraction of the original density of the liquid water. So what that means is if you had a sample of water, and let's say it occupied 1 milliliter of volume, if you boil that off to a gas, that volume would increase to 1,500 milliliters. So that is a huge change in volume. So just to note again that liquid water is very much more dense than gaseous water. Now, this difference in density between liquid state and gaseous state is pretty much true for all substances. So you can see for benzene here, the density for liquid benzene, which is 0.879 grams per mil. For solid benzene here, it's a little bit higher, but again, for gaseous benzene, it is much, much lower. With carbon tetrachloride, another substance, same deal, that the density of the gas is far, far lower than the liquid. And in general, for any substance, what you'll find that the gases are from like 1/100th to 1/5000th of the density of the corresponding liquid. Okay, so here is sort of a mini periodic table, and this sort of nicely points out that at room temperature, most of the elements are in the solid form. You have a couple of elements in the liquid form, and then you have about 11 elements in the gaseous form. So the elements in the solid form at room temperature are in gray. And so all these elements here, which includes almost all the metals and some nonmetals, these elements at room temperature are in the solid form. Now, there are a couple of elements that are actually at the liquid form in room temperature. So one of these elements is bromine here, so I'm going to just put a red spot there. And then the other element is mercury. So these are the only two elements at liquid form at room temperature. Now, there's another element that if you rose the temperature to that of blood warmth of 37 degrees Celsius, it would melt into a liquid, and that metal is gallium. But what I really want you to notice is which elements in their elemental state are in the gaseous form, and those are the elements in blue. So it includes all the noble gases here, and then it includes 5 of the 7 elements that we discussed earlier were diatomic at room temperature. So it includes hydrogen, nitrogen, oxygen, fluorine, and chlorine. So again, most elements are in the solid state at room temperature. There are a few that are gases at room temperature, and then there are only 2 that are liquids at room temperature. So another thing that I think is useful to know if you're going out into the real world is you need to know what the composition of air is. And so as you probably know, what air is a mixture of gases. And so I think it's good for you to know what the major gases are in the atmosphere. And so they are nitrogen and oxygen. And so nitrogen comprises about 78.1% of the molecules in the air. Oxygen comprises about 21.0%, and then argon is almost up to 1.0%. And then there are traces of the other gases that you can see in the chart. So one interesting question to ask is, does this composition of the air change depending on where you are? And the answer is no. If you are at sea level, what you'll find is that the composition of the air for each individual gas does not vary very much. It only varies about 0.1%. So that composition is pretty stable. Okay, so moving on. So now what we need to do is focus in on one of the properties that we usually measure for a gas. That property is that of pressure. So what I need to do is sort of talk about what the difference between the pressure of a gas is and what the force of a gas is. And so I think sort of a fun way to sort of understand the difference is to compare both the force and the pressure that are applied by a 14,000 pound African elephant versus a 120 pounds ice skater. So we have the African elephant in the left. It weighs 7 tons, which is 14,000 pounds. Now, what is the force that this African elephant is applying on the ground? The force is the same as the weight. So the African elephant is applying 14,000 pounds to the ground, so that is the force. And then the skater there, the weight is 120 pounds for the skater, and so she is applying 120 pounds of force on the ground. So clearly, the elephant is applying a lot more force on the ground. I guess it's what, something like 100 times more. Now, what is the pressure that both the elephant and the skater are applying on the ground? To figure out the pressure, what you have to do is you have to take the force and divide by the area by which that force is being applied on. So for example, let's look at what the pressure that the African elephant is applying on the ground. The way you would do that is you take the force of the elephant, which its weight is 14,000 pounds, and then what you do is to figure out the pressure that is being applied on the ground, you divide that 14,000 pounds by the area in which that 14,000 pounds is being applied on. And so that area would be the elephant's 4 feet. And so we have an elephant here with 4 feet, and each foot occupies an area of 250 inches squared. And so you can figure out what the pressure that this elephant is applying on the ground is when you take that force of 14,000 pounds and divide by the area that is being applied on, which is the 4 feet, the pressure that the elephant is applying on the ground is 14 pounds per square inch. Now, let's look at the skater. We already know that the skater is applying about 100 times less force onto the ground. But how much pressure is she applying on the ground? We can do the same analysis. We take the weight of the skater and then we divide it over the area in which she's applying that force on the ground. And so that area is that of the skates. And so each skate is, I guess, about 2 inches squared, which is not a lot of area, and there are 2 skates. And so if you calculate the pressure that the skater is applying on the ground is actually 30 pounds per square inch, which is over double that of the pressure that is being applied by the African elephant. So what pressure is, it's a measure of force over the unit area, and there are a couple ways you can increase pressure. You can increase the force over the area which is applied, or you can use the same amount of force and just reduce the area which is applied, and so that would increase the pressure. Now, which one is going to more likely fall through thin ice? Well, the one that has the most pressure on the ice more likely to fall through. So if you have an elephant trampling away across the ice and you have the skater there going across the ice, the skater is more likely to fall through thin ice is because the skater is applying more pressure on the ice. Okay, so let's move on. Okay, so what is sort of the molecular explanation of pressure? So let's say we have a sample of air, and we know that sample of air has a pressure. And so how do we understand the pressure that is given by those air molecules? Well, you have to keep in mind that every individual air molecule is striking a surface with a certain force, is doing it over a certain area, and so it's applying a certain pressure. Now, to understand what the pressure of all the air molecules are, you have to add up all the pressures of those individual air molecules, and that will tell you the pressure that is being applied by the sample of the gas. Now, it doesn't seem like air pressure is very much. The reason why it doesn't seem like it's very much is because we never feel air pressure for the most part. But here's an interesting fact. If you were to put your thumb on a table and then you were to place a bowling ball on the tip of your thumb, the amount of pressure that that bowling ball would put on that area of your thumb would be equal to the amount of air pressure in normal atmospheric air. So the question is, why don't we feel that weight of bowling balls on our skin? And the reason is because the pressure that is being placed by air pressure on our skin is being counteracted by the pressure within our cells that is pushing out. And so we don't feel a thing. So you have to keep in mind, if you were to do this experiment where you were to stick a bowling ball on your thumb, really you would have two kinds of pressure. You would have the regular air pressure, which is 14.7 pounds per square inch, and then you would have the pressure of the bowling ball. Okay. So the last thing I want to mention is you should have some idea on the instrument that measures pressure. And so the instrument is called a barometer. And so the way a barometer works is that you have a dish of liquid, and into that dish of liquid you put in an evacuated tube. It doesn't matter what the liquid is. So on the left side here we have mercury being the liquid, and on the right side here we have water being the liquid. So how does the barometer work? So what you can imagine is if you have a dish of water and you stuck a long glass tube that was evacuated, it had no air in it, as soon as that tube entered the water, you know that the water would go up the tube a certain distance. And in fact, if you are at regular air pressure, that distance is constant. And that distance that the water rises is about 33.9 feet, which is about 3.5 stories. So that's pretty high. So the question is, why is the water rising that high in the tube? And the way we tend to think about this is that air pressure is being put on the water, and this air pressure is being transferred through the water, and it's pushing up on the water of the tube. So the pressure that is being transferred through the water into the tube is supporting that weight of water there. Now imagine what would happen is if you increased air pressure. If you increase the air pressure, if the air pressure was greater, then what would happen is the level of water in the tube would increase. More pressure is being applied to the water, and it can support a greater height of water in the tube. You can do the same thing but with mercury. And so if you do mercury as a liquid, it will work by exactly the same principle, except the mercury will not go as far up the tube as the water did. And the reason is this: although with the mercury barometer and the water barometer, you have the same amount of air pressure, the air pressure will support as much weight of mercury as it would weight of water, but the mercury is a lot denser. So you cannot really get a lot of volume of mercury supported by atmospheric pressure. And so the height of mercury that is supported by atmospheric pressure is a fraction of that supported by water. So air pressure can support a column of water about 33.9 feet high. It can only support a column of mercury at 2.49 feet high, which is about 760 millimeters. If the air pressure increases, then you could increase the level of the mercury in the column. It can go up to like 761 or 762 millimeters. If like a storm comes by and the air pressure drops, then that air pressure cannot support as much height of mercury as with just regular pressure. And so that might go down to 740 or 730 millimeters of mercury. So the final thing I want to mention is some units that are commonly used to measure pressure. One unit that is often used is something called the millimeters of mercury, which I was just kind of talking about. And so normal atmospheric pressure has 760 millimeters of mercury. we now use millimeters of mercury as a standard unit of pressure for other pressure measurements. Now, you can also use torr as a unit, and the thing you have to keep in mind here is that 1 torr is equal to 1 millimeter of mercury. Another unit of pressure that we commonly use is a unit called the atmosphere. That has been defined in that 1 atmosphere of pressure is equal to 760 millimeters of mercury. That's something you'll probably have to memorize. Now, the SI unit for pressure is a unit called pascal. You do not need to know much about the pascals. It would be good to be sort of vaguely aware that there are a lot of pascals in the atmosphere. There are over 100,000 kilopascals in an atmosphere. So thank you for listening to that, and we will see you next time.